Hello everyone, my name is Ricardo Antonio Mendez Mendoza, and today I'm going to talk about my poster, which is titled Knox Scheme as a tool to interpret optical intervalence charge transfer processes. This study is around bimetallic compounds, also known, which have a mixed valence where the two of the species, usually where the donor and the acceptor, usually a pair of metal cations, have more than one available valence number, or in how we manage it, how we use it, the oxidation number. And between them, according to Hoche theory, there's an electron transfer from one side to the other. This electron transfer is reflected in the absorption spectrum as an absorption band, usually in the infrared region. And what we found is that this absorption band of between both donor and acceptor metals can be related to the charge transfers of one of the metals to the ligand, but also between two of the ligands. This was done using a Cartesian planes, the Knox scheme, as we will see below. Now, according to Marcus' theory, the electron transfer can be represented from the reactants to the products by two potential energy curves, as shown in the figure on the left. And this electron transfer is related to the reorganizational energy, the H21, and the free energy of the electron transfer related to the oxidation and reduction potentials. And between them, there is a barrier that the reactants have to overcome, called the thermal energy, the delta G hash. But what Hoche did was relate the reorganizational energy and the free energy to the optical absorption band, called E21 in this case. The equation shown here is the expression used and found by Hoche, and on the right is the same expression expressed in wave numbers, centimeters -1. In the case of the first transfer, optical intervalence charge transfer that was found was between two iron cations, where between an iron +2 and an iron +3, but in the case of the iron +3 is an isotope of iron. And now, how does the intervalence charge transfer occur? It can happen by two methods: by direct superposition of orbitals between the donor and acceptor, shown on the left, or through a bridging ligand, shown in the middle, through an oxygen ligand in this case, by the proper orientation of each of the involved species of the molecular of the atomic orbitals. On the right, this process occurs through a superexchange, where the ligand transfers an electron to the acceptor metal, in this case metal 1, and in turn the ligand accepts an electron or receives an electron from the donor metal, in this case metal 2, which can be seen as a sum of two transitions. Now, if we represent these transitions, all the possible transitions in a bimetallic complex, this in a Cartesian plane, where the coordinates represent the total oxidation number of the bimetallic complex, we can find what we call the Knox scheme, where connecting all the coordinates with the same oxidation number, overall oxidation number, we find what we call isoelectronic surfaces, where the bimetallic complex can travel along by optical electron charge transfers between the involved species. In this case, it's for a bimetallic complex with only one ligand involved, but it can involve two ligands. Now, by the color scheme, the green transitions correspond to metal ligand and ligand metal charge transfers that happen in the visible region. In the infrared region, it's commonly located the intervalence charge transfer or metal to metal charge transfer. And in the high energy, the ultraviolet region, we find the ligand to ligand charge transfer. How do we find this assignation? Well, what we did was, um, I'm sorry, what we did was expand the free energy term for the original equation of Hoche. We expanded the terms for the oxidation and reduction potentials of the ligand or ligands, and we also expanded the reorganizational energy of the bimetallic system has the sum of the reorganizational energies of each of the other transitions, in this case metal ligand, and ligand metal for a single ligand. If the process involves two ligands, as shown in the figures above, there is a third term, the transition between both ligands, which considering that metal charge transfers are usually located in the infrared region, we find accordingly that the ligand-ligand charge transfer is located in the UV region, in the high energy region. And by analyzing another charge transfer between the cases of zero difference between the oxidation numbers of the donor and acceptor, but also for one electron of difference, we find that a difference of two electrons is located between the UV and the visible region, and correspondingly that a difference for three electrons is located in more lower energies than the mostly known intervalence charge transfer. Now, we can represent this in the Knox scheme that we shown, but at transversal cuts by the same colors previously mentioned, and we find trends of where the transition is located for a broader amount of pairs of donor and acceptor oxidation numbers. How did we analyze or prove this theory, or some of the developments of this theory? We did so by using Prussian blue, which is one of the most known homo-bimetallic complexes in the field. This is the product of two iron species. The first one is an hexacyanoferrate species, in this case iron plus 3, and iron chloride, in this case iron plus 2. The result is a frame that connects both iron species through the cyano ligands, and in this case the species has a characteristic blue color. The blue color comes from the absorption spectra of the compound, which is located at around 14,000, almost 14,697 wave numbers, or 680 nanometers. And using the this characteristic along the full width at half maximum, shown here, again in wave numbers, we can calculate an approximate value of the oxidation and reduction potentials of the donors, which is for 0.75 volts. The experimental value is 0.7 volts, which shows that there's a strong, there is a close approximation between both values, one obtained experimentally through electrochemistry, and the second one obtained through optical measurements and UV absorption. Now, in the left figure, we have the cyclic voltammetry of the Prussian blue and there we can see the two characteristic bands, the oxidation and reduction waves, I'm sorry, for the compound, the reduction wave at around 0.2 volts and the oxidation wave at around 0.9 volts. But according there is a third wave located at approximately 1.10, 1.15 volts. It's kind of hard to see because its magnitude is smaller than the other two. And thanks to it, we can calculate and approximate, well, we propose that this oxidation wave corresponds to the oxidation of the ligand, in this case the cyanide ion. Now, considering that the ligand to metal and the metal to ligand equations are the same that for the original Hoche equation, we know three of the terms, in this case the absorption maximum, the full width at half maximum, and the difference between oxidation and reduction potentials. So what we did is calculate a new value for the denominator in the reorganizational energy term that is equal to the full width at half maximum squared over 2310. This is for the Hoche theory, from the Hoche theory for two metals. What we did is recalculate this value, but correspondingly for the ligand to metal charge transfer, and we obtained a higher value, 2504. Is the initial limit in which the free energy and the BLM, in this case, term, the numerator, are shown here, while the closest approximations are for the free energy, the absorption maxima over 4, and the BLM term, 1.4 times the full width at half maximum squared above the wave number of the absorption maximum. Now, additionally, considering that the absorption maxima for the metal to ligand charge transfer is located at approximately 5,000 wave numbers, we found that the corresponding transition for the ligand to ligand charge transfer between two cyanide ions is approximately at 61,000 wave numbers. This is located in the UVC region. Another species that we analyzed using this expanded scheme was the Kreutz-Tabbe ion. In this case, consists a pair of penta-amino ruthenium ions, +2 and +3, connected through a pyrazine ligand. And in this case, all we needed to, well, the main focus is that the ligand to ligand charge transfer is already reported. Using the relationship for the ligand to ligand, metal to ligand, and ligand to metal, we find that the approximate value of the metal to metal charge transfer is 1,312 nanometers, or 6,913 wave numbers. If we move slightly the ligand to ligand charge transfer, just 7 nanometers in this case, we find a closer value in terms of wave numbers compared to the experimental value with a mere difference of 35 wave numbers. Similarly, if we use the previous approximations for the free energy and the denominator term for metal to ligand and ligand to metal charge transfers, we find that the oxidation potential of the pyrazine in this complex should be at around 1.14 volts and its reduction potential at minus 0.41 volts. This opens interesting ideas because now we can find approximate values of the electrochemical oxidation and reduction potentials between the metals, but also for the ligands, using only the absorption spectrum of the system. Unfortunately, more experiments need to be done because we don't know if there are trends in these values of BML and BLM, depending on the ligands, metals, complex structure, or if we can just simply propose a general value, as we did in this case. Thank you very much for your attention, and I hope to see you in person very soon.